Hello class. Let's start 3.5. So the big idea in 3.5 that we're going to start off with is talking about a subspace. And the book doesn't do, and these slides don't do a great job of motivating a subspace. Like, why talk about a subspace? Be nice to explain a little bit of a why. It's going to end up giving us a better way to talk about when situations when we have a system that has a solution and when we have a system that doesn't have a solution. So we'll end up calling something a null space, and that's related to something when linear systems do not have a solution. The idea of a subspace or a space is when you're in a world where no matter which vectors you take linear combinations of, you stay in that world. That sounds a lot like a span, and it turns out spans are subspaces. The spans of vectors are subspaces. So you might be wondering, like, why come up with a different name? It does allow us to connect to some other mathematical ideas that are important. Some ideas that are important in the larger the mathematical community. And it allows us to be a little bit more technical in some ways. But okay, let's dive in. So a subspace of Rn is any collection S of vectors in Rn that has these three components. So it needs to have the zero vector. Any two vectors, u and v, if you add them together, that's also in the that's also in S. That's also in the subspace. And if you take a scalar multiple of any vector in there, it's also in the subspace. Now notice these just corresponds to all possible linear combinations. So these two are just all possible linear combinations. So if all linear combinations are in that space and we have the zero vector, then we're in that space. The zero vector has to be in there because one of the scalars you could pick is 0. So 0 times a vector is just the zero vector, and so you need to have that in there. So these are three criteria. So technically you don't need that first one if you understand that the scalar could be 0 here. But it's important for us to check. So they put it as its own criteria to make sure we check and make sure it's there. So if we have problems where we're trying to figure out if something is a subspace, then all we need to do is to check these three things. So that's what it says right here. So we just have to check the above three conditions. And all of them have to hold for it to be a subspace. So first example is the zero vector. The set containing the zero vector. Is that a subspace? Well, does it have the zero vector? Does it have the zero vector? Check. So zero vector. Zero vector. Check. Is it closed under addition? So that's another way of saying this other one. Closed under addition means if you take any two vectors in there, if you add the vectors, is it still in the set? Well, the only vectors we have are the zero vectors, so we can take two copies of the zero vectors, add them together, and we get the zero vector, and that's in the set. So closed under addition, check. And what about closed under scalar multiplication? I'll just call that C times. Well, if you multiply the zero vector by any scalar, you get the zero vector. So and the zero vector's in there, so check. Okay, kind of a boring example. Is the line L given by y equals x plus 2 a subspace of R2? Is the zero vector in there? No. So at x equals 0, you get y equals 2. So you don't have the point 0, 0. That's this origin right there, 0, 0. It's not in there. So we actually don't have to go any further. Since the zero vector is in there, we know it doesn't work. But just to illustrate how the other things can be problematic, if you take, here's one vector that points to a value on that line. If you double that, if you take that vector and add it to itself, it's not on that line. And if you multiply it by 2, which is the same thing, you don't end up on that line. So with addition and scalar multiplication, then we don't end up there. Even if we called this v right here that points to this point, and u, and add them together, we're going to have some point out here that's not on that line. So we're in trouble. This is not a subspace. So is the line given by y equals 1/2 x a subspace of our square? Well, is 0, 0 a point in here? Well, if you plug in x equals 0, you get out y equals 0. Good. So it does have the origin. So check. If u and v are any vectors on the line, is u plus v also on the line? Yeah. If we take any vectors from the origin out on this line, no matter where we go, and we add them, we're still going to end up on the line. The one example they've done here is there's u and here's v, and so we're going to end up, if we take this u, put at the end of v, you get to this point, and that point is still on the line, so you can draw a vector from the 0 vector, or the 0 coordinate to that point, u plus v. So check. And if we scale a vector, will it be on there? Yep. We can. If you think of another way to do this is to rely more on the equation than just the geometry of stuff we know before. But you could say, what if I plug in cx for x? Then what do you get out? You get out. That's going to be the same as 1/2 c. Then you're going to get out. Y is 1/2 c times that x. And I have a better example later on where we'll do this with the equation. Sorry. Okay. So the line W is a subspace, and any line through the origin is a subspace. Like vectors that live on there, any combination of vectors that live on that line, any combination of vectors in the line still lives on the line. Okay, show that the plane P defined by the equation x plus 2y minus z equals 0 is a subspace of R3. So this does define a plane in R3, but we need to show that it's a subspace. So first, does it include the 0 vector? If 0, 0, 0 is this in there? So if x equals 0, y equals 0, and z equals 0, is this true? And it is true. 0 plus 2 zeros minus a 0 equals 0. So we're good. So check on number 1. What about closed under addition? Well, let's take 2 points here. Let's take x1, y1, z1, and let's take x2, y2, z2, and these have to lie in this plane, so that means that x1 plus 2y1 plus z1 has to equal 0. Since it's in the plane, it is the all points x, y, and z, so where you can take that combination and get 0. And that also means x2 plus 2y2 plus z2 equals 0. So what happens if we add these two together? So x1, y1, z1 plus x2, y2, z2 equals x1 plus x2, y1 plus y2, z1 plus z2. We get that vector. Is that we have to show that that's still on this plane. Well, we can let's plug it in to our formula up here. So for x, oops, I made a mistake. That should be 2. So x1 plus x2 minus 2. I'm plugging in my y's here. So that's y1 plus y2 plus or minus, actually, minus z1 plus z2. Does that equal 0? Putting a question mark there, we're not sure. So let's see what this left side equals. Well, I'm going to distribute out and combine all the like terms. It would be nice to see if I can combine all the subscripts with 1s together and the subscripts with 2. And so I get x1 plus x2 minus 2y1 minus 2y2 minus z1 minus z2. And still don't know what that equals yet. Then I'm going to combine all the 1s with subscript 1. So x1 minus 2y1 minus z1. And then plus x2 minus 2z2, oops, y2, and minus z2 equals, well, this we know equals 0 from up here, and this we know equals 0 from right there, so that's got to equal 0. Because we have a 0 plus a 0. So it is true. So that's closed under addition. What about closed under scalar multiplication? Well, you can do a similar thing, but you substitute in cx1, cx, some constant times x1 for your x coordinate. Did I make a mistake? I did. That should be positive. Positive, positive, positive. Positive. There. Sorry about that. cx1, cy1 plus 2c y1 minus c times z1. Does that equal 0? So I'm thinking of just an arbitrary point that's on this line, assuming that it's on this plane. Just call it x1, y1, z1 and take a constant multiple of it, but that's the same as just taking c times each of the entries. And if I plug it into that formula, then I can factor out a c, and I get c times x1 plus 2y1 minus z1. And since I know this much equals 0, then I just get c times 0, so that whole thing has to equal 0. So that's also on the plane. So check, check, check. Got checks on all 3 criteria. So here's the connection to span that I mentioned before. If you have a set of vectors in Rn, then the span of those is a subspace of V. You can take 0 amount of all of them and get the 0 vector. The span is all possible linear combinations, and so any 2 vectors, if we take any 2 vectors that are in the span of there, then the linear combinations of those have to be in there, because that's the way span is defined. Here's a technical way of looking at it. And linear combinations also, you can have the constant multiple there. So if you take any 1 vector in there, then you multiply it by the constant, it's still in the span. So the span is a subspace. Sorry, I know I'm going through this quick. This is something you can go back and look more carefully at. Okay, here's an interesting one. Does the set H form a subspace? And H is all of the vectors of this form where for any t and r. So it's easiest to split them up. So here we have we should recognize this as the equation of a plane in vector form, and where t and r can be any real numbers, so that's really the span of these two vectors. And so the span of, and we already know the span of any set of vectors is a subspace. So we're using the theorem there and not going back to the definition. So I think I'm going to skip this example for now. It's not something you'll need on your homework. So yeah, I'm going to skip those two. We can do those examples like that in class. So a subspace satisfies those three criteria. Lines through Rn are examples. Planes through Rn, planes in Rn, through the origin. Gotta emphasize that. And a span of any set of vectors in Rn. All subspaces, we'll see, are actually of the form where you can write them actually as a span of a set of vectors. So here we're going to talk about some specific subspaces of a matrix. So let A be any m by n matrix. The row space of A, so we call it the row, and then we put these parentheses around it. This means row space of A, is the subspace of Rn spanned by the rows of A. So the rows so this is a 2 by 4. So if we're thinking of rows, then we're in Rn. Because we have 4 coordinates for each of these rows. So I'm sorry, we're in R4. So because we have 4 coordinates in each of these rows. Okay, we have two vectors in R4. So that's why it's Rn. Notice the second, n is the number of columns, but it's the dimension of the row space. It's not the dimension, but it's the space that the row vectors live. They live in Rn, even in R4. So the column space of A is the subspace of Rm spanned by the columns A. So the columns are 2 coordinates. We have 2 coordinates for each of these, so they live in R2 in this example. So we have 4 vectors in R2. So we can either think about that matrix as 4 vectors in R2, or we can think about it as 2 vectors in R4. So key things, the dimensions of the span will be the same in those things, but one can be linearly independent and one can be linearly dependent, so you have to be careful. The number of pivot positions would be the same if you row reduced. Okay, so we think about A as we can think about A as the columns with lower a, or we can think about it as m rows with capital A, and the row space of A is the span of all of the rows, and the column A is the span of all the columns. So in this case, we can think about the span, in this case up here. So column of A, for example, if we call this A, is the span of 1, 5, 526. Adobe just doesn't like this as much. 526 37, etc. 48. Okay, and the row space of A would be the span of 1, 2, 3, 4, and 5, 6, 7, 8. Okay. And that's what these are saying down here. Okay. So here we have a specific A is V in the column space of A. So if we rephrase this question in things that we already know, are there linear combinations? Or we could say, is V in the span of these columns? And that means, is there some linear combination of these columns that equals this? Then you can do that by doing row reduction. You can just set it up as an augmented matrix and start row reducing. And as long as you've got this row is not a linear multiple of this row, it's not a scalar multiple. So the rows are linearly independent. So I have two, we will have two pivot columns. So I'll be able to span R2. So this will be in there. So that's one way to reason through that without actually having to do the row reduction. And yeah, this is where we could work out and do the row reduction, but because we only have two things, we can just see if we're going to have two pivot positions, and we know we do because they're not linear multiples of each other. Okay, so this is a new, so what about the row space? So this is one thing we haven't done before. We want to know, is there a linear combination of these rows that can get to this one? And we could transpose them both, and then it's just the same question that we were doing before, where we have questions about a column space. 1, 3, a -1, 2, 0, 1. We could rewrite it like this: 1, 9, a -2, and then we can row reduce. And if there's exactly one, if this is consistent, so if there is a solution, then V is in that row space. The book does teach another way to do this. You don't have to do the transpose. You can write it this way, and they augment it at this bottom part. They do it this way, and so if you can do row operations, of this matrix and get a row of zeros at the bottom, then V is in the row space. That bottom row, that vector that we augmented it with here in the row, then it is in the row space. And the reason is, if you can make this bottom row 0 through row combinations, through row operations, that means through operations you've taken these two vectors, these two row vectors, and made a combination of them to equal a -1, a -9, and a -2, and add them together. So you've created a combination that can cancel that out. So then you just change the signs of those scalars that you needed in those row operations, and you could make that vector. So that's one way to reason through why that works. So in your WebAssign homework, you'll see them talk about it this way, okay, and not as much this way. So written homework, you're free to choose. Okay. So here's A. Find a description of the column space of A. So here we can start row reducing. What we need to figure out is if these are linearly independent. If they are, then we could just say, oh, the span is 1, 2, 3. We can say this at the beginning anyway. 1, 2, 3, 1, a -1, 0, 0, 1, 1. We could say that, and that's true, but it hasn't been very helpful, because how many dimensions is that? Is that a one-dimensional too? Is it a line? Does it span a plane in R3? Does it span all of R3? We don't know. So we can start by row reducing. So okay, I saved some time by pausing and then writing out some work. So what I did was I augmented that matrix with just an arbitrary x, y, and z, trying to figure out what points we could actually get if we spanned that. And if A ended up being invertible, we'd be able to get anything, because our independent, our columns would be linearly independent. We know it would span R3. But as we can see, as I started to row reduce, in that coefficient matrix, I've got two rows that are the same, so I end up with a row of zeros. Now this is something we haven't done one of these examples where we've just put x, y, and z over here, but you just do row operations the same. And one thing that happens is we get this bottom row down here, and this will have a solution only if z minus x minus y is 0. We have two pivot columns. We have one free variable. So we're going to end up spanning 2 of the 3 dimensions in R3. So we're going to span a plane. And we can rewrite that as an equation. I'm going to rewrite it the way we would, kind of a more standard way here. We could rewrite it this way. And that is the equation of the plane that is the subspace of the column space of A. So it is the column space of A, or the subspace of Rn. So this is another way to find equations of planes, by the way, that you span. Okay. I think we'll stop right there, and we'll continue next time. Thanks.